Welcome to another session of basic mathematical analysis class. Today we will going to discuss how we can represent a complex number in a plane, or if such a representation is existing, we will say that the plane is to be a complex plane. Complex plane. First of all, we have said that a complex number. For example, we can take a complex number as, for example, we can take the complex number z equal to 3 plus 4i. It's a complex number with this as the real part, and this one 4 is said to be the imaginary part. We have discussed this already. Now this complex number can be written as 3 comma 4 times. So this evidently will represent a point in your Euclidean plane. Now we can have this point. Suppose you are drawing x and y axis, and 1, 2, 3, 3, 2, 1, 0, and this here also you can mark as 1, 2, 3. Suppose this 4. Now 3, 4 means we know evidently this is going to be the point, this point, right? So this is the point 3 comma 4. So in the same way, we have said that 3 is going to be the real part and 4 is the imaginary part. So instead of this x-axis, we can consider this as the real axis. In a similar fashion, this y-axis can be taken as imaginary axis. So instead of x-axis and y-axis, we have got real axis and imaginary axis. Now we can easily plot any complex number in this fashion. Now this plane is called the complex plane. So a complex number z equal to x plus iy is uniquely determined by an ordered pair of real numbers x comma y. The first and second entry of the ordered pair corresponds to the real part and imaginary part. Now for example, here you have given one more example, 2 comma minus 3. 2 comma minus 3 in the same fashion we can represent 2 comma minus 3. So here is 2 and minus 3 means it will come down, right? So this is going to be your 1, 2, 3, of course minus. So this step 2 comma minus 3, 2 comma minus 3 means somewhere here will come. So this is the point, 3 comma minus 3, 2 comma minus 3. So this would represent the complex number 2 minus 3i. 2 minus 3i. So this is the definition of complex plane. See, set plane or complex plane. This is called set plane or complex plane. That is imaginary axis, real axis, and you can plot any point like this. So another way of representing this complex number is like this. See, here you have represent this as 2 comma 3, but you can have from here a vector. Okay, this of 2 comma 3 comma 4. So you can either represent a complex number as an ordered pair or as a vector. So next thing is vectors. So as I said, we are representing the complex number z equal to x plus iy as a vector. Just we will say that position vector. Now if this is the position vector means vector, we know that we can go for its length or the magnitude, right? So what should be this distance? Like that we can consider. So instead of considering the distance, we can have, see, what is this distance now? This is y and this is x. Now what should be this distance? We can easily say that that is going to be x square plus y square, square root of. Now we will say that this distance, at first we have said that a complex number can be expressed as a vector like this. Now length of that vector is, we will say this is the modulus of Z. So that is the next thing. So you can read this in other courses. Okay, seeing the number is an ordered pair of real number can be interpreted as a component of a vector. Thus, a complex number z equal to x plus iy can also be viewed as two-dimensional position vector. That is, the vector whose initial point is the origin and whose terminal point is the point x comma y. See this figure? Like this. Now we can easily calculate what is this length, and this length is called the modulus of z. So definition, the modulus of a complex number z equal to x plus iy is the real number mod z equal to square root of x square plus y square. Or else we can say that modulus of a complex number mod z is equal to square root of real part square plus imaginary part square. So this is the definition of complex numbers modulus. This is also called absolute value of mod z. Sorry, absolute value of the complex number z. For example, as we have considered previously, take the complex number z equal to 3 plus 4i. 3 plus 4i. Now what should be its modulus? We want to calculate mod z. So mod z means you can compare this with x plus iy, and if this is the condition, we are having square root of x square plus y square. So instead of this, you are having z equal to 3 plus 4i. Now mod z is equal to square root of 3 square plus 4 square. So what should be? It should be square root of 9 plus 16. You will get square root of 25, and that is nothing but 5. So since we are taking the distance, we should take only the positive thing. So modulus means it's always positive. So we are taking it as positive 5. So 3 plus 4i, if the complex number is 3 plus 4i, its modulus is nothing but 5. Now we will have some discussion on the absolute value of a complex number or the modulus of a complex number. So properties. For any complex number x plus iy, the product z bar is the real number that we have already seen, right? Then specifically z bar is the sum of the squares of the real and imaginary part of z. That is z bar equal to x square plus y square. You can easily have, what is z? Z equal to x plus iy. And z bar means we are taking the conjugate. Conjugate of x plus iy, x minus iy. Now we calculate what is z bar. Z bar means x plus iy into x minus iy. We have already seen this, how we can multiply. So we will take component wise. So first part should be x into x square. Next term minus I into xy will come, x into this term. Next you will multiply this with this. So you will get plus I into xy, right? First term. Next minus iy into iy. I into I you will get minus 1. I square minus 1. So it will become plus y square. So this term and this term get cancelled. So whatever remaining is x square plus y square. So thus z bar is nothing but x square plus y square. Now square root of x square plus y square, we will say that is going to be the modulus value or the absolute value of z. So in particular you can write mod z square equal to z bar, right? Mod z is equal to square root of x square plus y square, and that's equal to square root of, see what is that, z bar. which implies modulus of z square equal to zz bar and modulus of z equal to square root of zz bar. Thus, the modulus of a complex number z has additional properties like this. What is this property? Modulus of z1 z2 equal to modulus of z1 into modulus of z2. Will it be true? Suppose you have got two complex numbers, z1 equal to x1 plus iy1 and z2 equal to x2 plus iy2. Two terms, right? Then you can have modulus of z1. Modulus of z1 means x1 square plus y1 square, and modulus of z2 means what it should be x2 square plus y2 square. So call this as equation 1. Now we will come across what is z1 z2. z1 z2 equal to z1 is x1 plus iy1 into x2 plus iy2. Now when we are multiplying, you will get this to be as x1 x2 plus I into y2 x1 plus I into y1 x2, right, plus I into I square minus y1 y2, right. Now this equal to, you can have this as x1 x2 x2 plus I into what it should be y1. Okay, we can have this real part together and imaginary part together. So we'll have this as x1 x2 plus minus, right, not plus, minus, it should be minus y1 y2 plus I into x1 y2 plus y1 x2. So in order to find the modulus of this means we will have modulus of z1 z2. Modulus of z1 z2 means x1 x2 minus y1 y2 all square plus, right, exactly it will come square root of, right. So let me put it as square. So this also square equal to this square plus x1 y2 plus y1 x2 square. Just you simplify it. It's of x1 y2 plus y1 x2. Okay, so when you are having this term x1 square x2 square minus 2x1 x2 y1 y2 plus y1 square y2 square, first term, right, plus x1 square y2 square plus 2 times x1 y2 y1 x2. This term get cancelled, this term and this term, plus whatever remaining is plus y1 square x2 square. Now you combine these two, so you get, usually you will get this term only, right. So you can easily get while simplification you will get, it should be the same as equation 1. This plus this you will get. Okay, that I'm leaving for you to work. Now if z1 and z2 both are equal, means what you're getting is, see, z1 z2 are equal, so modulus of z1 square equal to mod z1 into mod z1 you will get, that is mod z1 square. So you can easily have modulus of z square equal to mod z1 square. Now again we can think this modulus as a distance. So the addition of complex numbers Z1 and Z2, just we have given, when stated in terms of ordered pairs, you can take this like this: x1 y1 plus x2 y2 equal to x1 plus x2 plus comma y1 plus y2. That is sum of real part and sum of imaginary part. So it is the component definition of vector addition. In geometrically we can represent like this. It is a vector addition. That is, if z1 is a vector is given, z2 is another vector is given. So in order to find z1 plus z2, what we are going to do? We will complete this parallelogram and take this diagonal, right? So the length of this diagonal is nothing but z1 plus z2. Okay, so that is nothing but x1 x2 comma y1 y2. This is how we will represent the sum of complex numbers. Now what about the difference? Suppose you want to get the difference, means we will take this diagonal. You have come across in your vector classes. Okay, we will take like this. Then this diagonal is going to be the difference. So in order to find the difference, z2 minus z1 can be drawn either starting from the, see, like this. Now the terminal point of z1, see, from here you're starting and ending at the terminal point of z2. So we should take the direction like this. Okay, z1 to z2. Ending at the terminal point of z2, or the position vectors whose initial point is the origin and terminal point is, or else you can translate this to here, right? Now this should be starting from the origin and the terminal point is x2 minus x1 and y2 minus y1. So this is how we will represent the difference of two complex numbers in a vector manner. Now distance between 2 points. Now in Euclidean geometry, we know the distance between 2 points x1 x2 x1 y1. See, this point can be taken as x1 comma y1, and this complex number can be taken as x2 comma y2. Now as we have said, we can represent this in our complex plane. So I have got 2 points here. One point is x1 y1, another point is x2 y2. Now I want to find what is the distance between these 2 points. Okay, what is the distance between these 2 points that I want to find? So what should I do? In order to find the distance between these two, as we are dealing in our Euclidean geometry, you can have it here also. So distance between means I should drop the perpendiculars, right, from here and here. Okay, now the total distance I know. Sorry for that. So we know the total distance, this distance and this distance. So from here this is x1, here to here the distance is x1. Now here to here the distance is x2, right? Now here to here this distance is y1, and from here, right, this distance is going to be y2. Sorry, this is y1, right, and this is y2. Oh, made a mistake. Sorry, this is y1 and this is y2. This is y1 and this is y2. Now similarly x1. Okay, now what about this distance? This distance, evidently this distance should be y1 minus y2, right? Now what about this distance? This will get I'll get total distance is x2. So x2 minus x1. So in order to find this distance, it should be square root of x2 minus x1 square plus y2 minus y1 square, right? So the distance between this, now actually this is nothing but if this is z1 and this is z2, means this is nothing but modulus of z2 minus z1, right? So modulus of z2 minus z1 can be taken as square root of x2 minus x1 square plus y2 minus y1 square. So when z1 equal to 0, any one of this complex number is 0, means you will get the distance from the origin, that is nothing but the modulus, right? So this is the distance concept in your complex class. So today we have discussed about how we can represent a complex number in the complex plane, and how we can represent the complex number as a vector. And when we are representing as a vector, how we are measuring its length or the scalar value of that vector, or the modulus of the vector, or we will say that it is the absolute value of the complex number. And next thing, we have seen that how we can represent sum of two complex numbers and the difference of two complex numbers in the complex plane. And the third one, we have calculated what is the distance between 2 points in a complex plane. So let me wind up here. Hope you understood today's class. So thanks for your patient listening. Thank you.